Hello, this is a lesson for section 1.1 of your intermediate algebra textbook, solving linear equations and inequalities. Our objectives for this section are A. Determine whether a given number is a solution of a given equation. B. Solve equations using the addition principle. C. Solve equations using the multiplication principle. And D. Solve equations using the addition principle and multiplication principle together, removing parentheses where appropriate. Let's begin with the definition of equation. An equation is a number sentence that says that the expression on either side of the equal sign represents the same number. So we say they're equal just as you would say, I don't know, $1 is equal to $1, right? They're the same. Example, determine whether the equation is true, false, or neither. So we have 4 plus 6 equals 10. Is that true? Well, yeah. 4 plus 6 is 10. 8 minus 3 is 4. No, right? That's false. X plus 9 equals 21. Well, neither. We do not know what the number x represents. What is this? Solution of an equation. The replacements for the variable that make the equation true are called solutions of the equation. The set of all equations is called the solution set of the equation. When we find all the solutions, we say that we have solved the equation. Determine whether 8 is a solution of x plus 12 equals 21. So our question is, can this number x, if I substitute that with 8, would that make the statement true? So we begin by writing the equation, and then we go ahead and replace that x with 8. 8 plus 12? Not quite, right? 20 is not the same as 21. Since the left-hand side and right-hand side are not the same, 8 is not a solution. Equivalent equations. Equations with the same solutions are called equivalent equations. The addition principle. For any real numbers a, b, and c, a is equal to b is equivalent to a plus c and b plus c. So do not let the use of a, b, and c throw you off. In math, in order to create a statement using any number that we can think of, we create letters or use letters so that we can hold this rule to be true for any number. So we're saying if I have a number, let's go ahead and pick a number. Let's say 3. If I have 3 and I'm saying it's equal, 3 is equal to 3. And what our rule is saying is if I add the same number to both sides, then it will still hold that equality. So if I have 3 plus 2, and I take my same 3 and I add 2 to the other side, to both sides, we see we get the same thing in return. And this is what the addition principle is saying. Now, even though it's the addition principle, it also works with subtraction. So as long as we have an equality, like we see here, I can add and subtract the same thing on both sides, and it will still hold true. Let's see an example. Let's go ahead and solve x plus x. X plus 6 is equal to negative 9. All right, so I want to find out what x is. And maybe just by looking at it, you can kind of think of what that number should be. But let's use our addition property. This says I can, so addition property. And this says I can add or subtract the same thing on both sides of my equation. Okay, so I want to get x by itself. So why don't we try and move that 6? Well, if I want to move it, if I want it gone, then I would need to make it 0. So what can I do to 6 to make it 0? Well, I can take the opposite, minus 6. 6 minus 6 is 0. Great, that would get rid of my 6. However, my addition property says that I have to do the same thing on both sides. So let's also subtract 6 from that 9. So I have negative 9 minus 6. And that gives us negative 15. I know subtracting with negatives might be a bit weird. A rule I always use is you always add the opposite of the second. So you change your subtraction to addition and you change the sign of the second. So negative 9 plus negative 6, that gives us negative 15. So we get, on this side of our equation, we're left with x plus 0, so that's just x. And on the other side of our equation, we're left with negative 15. So our statement is x equals negative 15. So we see here that same work I have, and our answer is negative 15. And we can always check our work. We can do so by plugging in our answer. So let's plug in a negative 15 for x. Negative 15 plus 6, yes, that does give us negative 9. Let's do another example. Let's use decimals. So same idea works. Even though we have decimals, don't let that throw you off. Feel free to use a calculator if you're a bit stumped or you don't want to do it by hand. So let's go ahead and use our addition property. So we're going to add the same thing on both sides. I want to get y by itself, and this number is a problem. So what can I do? I can take the opposite and do it to both sides. So since it's being subtracted, negative 17.9 right here, I can go ahead and add it to both sides of my equal sign. That way, negative 17.9 plus itself will give me 0. And then I can clean it up a bit. Negative 8.3 plus 17.9 gives us 9.6. That's on my left-hand side of my equal sign, and on my right-hand side, I'm just left with y. So we have an answer. And you can always check it by plugging it back in. So let's let y be 9.6. And is that true? Yeah, you can use your calculator and check it out. Multiplication principle. It works the exact same way as your addition principle. It reads, for any real numbers, a, b, and c, where c is not 0, a is equal to b is equivalent to a times c is equal to b times c. So again, don't let the use of letters scare you. We just use them to say, hey, for any number or any real number, this rule works. Okay, so let's use numbers to talk about this rule since I know letters can be a bit weird. So let's take 3 again. We have 3 is equal to 3. Well, our rule is saying if I multiply the same thing to both sides, it's still the same. So here we see we're going to multiply the same thing on both sides. So take 3, now let's multiply by a 2. 3 times a 2. 3 times 2 is 6. And 3 times 2 is 6. So we see we still get the same thing in return. Now let's talk about real numbers. What is a real number? It doesn't refer to like a fake number or a real number. Real number includes 0, whole numbers, both positive and negative. It includes fractions and decimals. That is a real number. And it also includes irrational. Does it include rational? Question mark. I'll get back to you on that. So these are numbers that we can work. The exception to our principle is not 0, because if you multiply a number by 0, let's say 3 times 0, our answer is going to be 0. So that kind of clears out our problem. So that's not a number we ideally want to work with in the multiplication property or principle. But notice, we can also multiply with fractions and decimals. And we'll see an example of that in our future slides. Let's move forward. Let's go ahead and solve this example. Solve 3 over 4x equals 15. I think I forgot the equal sign. All right, so our goal is, let's try to get this x by itself. Let's get it alone, because we want to know what x is equal to. The way we can do that is by getting our variable by itself. But that 3 over 4 fraction is a bit of a problem. So what can we do to simplify it? Well, what we can do is we can multiply by what's called the reciprocal. And a reciprocal is just the flip of a fraction. Flip of a fraction isn't really a correct term. We say reciprocal, but that's a good way to help you remember. So since we have 3 over 4, what would be the reciprocal? The reciprocal would be 4 over 3. And why do we aim to multiply by the reciprocal? That's because if we multiply by the same fraction flipped, we see that they give us 1 in return. 3 divided by 3 is 1, 4 divided by 4 is 1, so we get 1 in return. All right, let's continue back into our problem. So we multiply by the reciprocal, and we see 4 gets divided by 4 to make 1, 3 gets divided by 3 to make 1, so we're just left with 1x, or just x. And then here we can clean up this fraction here. Remember, we multiply fractions across? Yeah, let me show this work over here. So I have 15 over 1 times 4 over 3. We multiply fractions across. 15 times 4, 1 times 3. I didn't multiply across because if we simplify it before multiplying, it makes it so that we have not so big of a number to work with. Now this division bar, or this fraction bar, means to divide. So we can divide here. We see 15 can be divided by 3. They can both be divided by 3. 15 divided by 3 is 5. And 3 divided by 3 is 1. So we're left with 5 times 4 in the numerator and 1 times 1 in the denominator, which is 20 over 1, so we just have 20. All right, so we get that x, or 1x, is equal to 20, and that is our answer. I know some of you might not be fans of working with fractions, but my only suggestion is take it one step at a time. The entire math class will not be fractions, but when we stumble upon them, just make sure to give yourself time to complete those problems. Let's do another problem. 6x equals 96. Well, we have our multiplication problem, and it says I can multiply the same thing on both sides. We can also treat our multiplication property as a division property, such as we can do for this problem. Our goal is to get x by itself, but we see it's being multiplied by that 6. What can I do to undo or get rid of that 6? Well, we can divide by 6. But remember, when I do to one side of my equation sign, I have to do to the other. So 6 divided by 6, that's 1. and I see it again on my other side. So I'm left with 1x equals 96 divided by 6. Let's punch it into our calculator. We get 16. All right, let's make sure that's true. 6x equals 96. Let's replace x with 96. I'm sorry, with 16, because that was our answer. And we see it holds true. So multiplication property / division property work out. Let's do another example. Even if we see a negative, if it's being multiplied, we still treat it the same way. So what we can do is we can divide both sides by our, well, our -7. So I think this slide has a typo. So we want to go ahead and divide by a -7, since we have a -7 in our problem. -7 divided by -7 is 1. And 84 divided by -7 will give us -12. So I have x is equal to -12. That is our answer. That's our solution. So we're left to ask, is it true? Let's go ahead and check it. So we have 7x equals 84. Let's replace x with a -12. And yes, it holds true. Now just recall, when working with your signs, a same sign multiplied by a same sign will give you a positive. So positive times a positive will give you a positive. A negative times a negative will give you a positive. And when you have a different sign, it'll give you a negative in return. So a positive times a negative will give you a negative. And these same rules work with division too. Just in case you were caught up as to what happened with those negative signs. All right, let's put this all together using both our addition property and our division property. So we did examples where we use each one of these separately. Let's do an example where we do them both together. So we have 9 plus 8x equals 33. Our question is asking us to solve. So this means get x by itself. That's what it means to solve. So we want to get x by itself, but it's within this term. So let's get that term, that 8x by itself. We can get it by itself by moving that 9. So we subtract 9 to both sides. And that will give us 0, so that's gone. And 33 minus 9, that gives us 24. All right. So we're there. 8x equals 24. All right, now we can use our multiplication property / division property. We can go ahead and divide both sides by 8. 8 divided by 8 gives us 1. And what is 24 divided by 8? We get 3. Now we got x by itself. And our answer, we have solved the problem, and our answer is x equals 3. And you can always check it by plugging it back in and working it out. And yes, it holds true. Let's do another problem that's a bit more involved. So again, we're being asked to solve, which means get your x by itself. Solve for x. How we would go about a problem where we have a lot of copies of x and a lot of numbers without an x. Start by cleaning up your problem. Simplify the problem. Get all the x's together, all your numbers together. So we can see we have our left-hand side and our right-hand side. In our left-hand side, I see I have several x's. Let's go ahead and add and subtract them. So we have 4x minus 6x. That gives us negative 2x. And we have that plus 7 still in our problem. In our right-hand side, we have a 10 plus 12. 10 plus 12, we get 22. And I'm left with just the 3x. Okay, we cleaned it up a bit. So what do we do from here? Let's go ahead and get our x's on one side and everything else that doesn't have an x on the other side of our equal sign. So let's start off by moving that 7. Let's subtract 7 on both sides. That way our 7's are gone. And now let's go ahead and get our x's together. So let's move that 3x. Let's subtract it to both sides so that it's gone. Negative 2x minus 3x gives us negative 5x. So we're left with negative 5x minus 15. Last piece, let's go ahead and divide by a negative 5. Negative 5 divided by negative 5 is 1. 15 divided by negative 5 gives us negative 3. So x is negative 3. Let's do one with decimals. Don't let this trick you or intimidate you in any way. Just go ahead and use your calculator if necessary. All right, so we see that we have a number with a variable, and our instruction is telling us to solve. So let's try to get this y by itself. Let's first get that term by itself. So let's subtract both sides by 18.4. Oh, before we do that, what we can do, if you don't like decimals, you can multiply by your largest decimal place. So from your decimals, you have your tenths place, tenths, hundredths, thousands, 10,000s, and so on. You multiply by 10 each time to get to a number. All right. So if you don't like decimals, what you can do is multiply by your highest base holder. So we see we have tenths place, hundredths place. So let's go ahead and multiply both sides by 100. This allows us to get rid of our decimal places. Remember, multiplying by 100 moves your decimal 2 spaces. And if you ever forget, you can always punch in your calculator and see how the number changes. All right, so we have 100 times 18.4 and 100 times negative 6.2, 100 times 7.24. Let's move the decimal over twice. That's what it's going to do. So we have 1840 minus 6, you move it over twice, 20y is equal to 724. We see that there. All right, let's get y by itself. So let's go ahead and move that 1840 to both sides. So minus 1840 so that it's gone. And now we have our term with the y by itself. Let's go ahead and divide by that negative 620. And we get as our answer 1.8. Let's do another example where we have several math applications. Here we see that we're going to be using our distributive property. So if we have parentheses on a number on the outside, we know to multiply that number out. So we have 8x minus 24, as we see here. All right, same idea. I want to clean up both of my sides, my right-hand side and my left-hand side. We see here that we can add a 6 to this negative 24. Now let's go ahead and get our x's and our constants, our numbers without a variable on one side. So let's start off by moving the 8x. So minus 8x, that's gone. Minus 8x. Well, what's going on here? Notice that our x's were in a situation where they added to make 0. And now we're left with a true statement. Negative 18 equals negative 18. So what does that mean? When we get a true statement, such as the one we see here, where half the same number equals itself, same number equals the same number, our answer is every real number is a solution. There are infinitely many solutions. That's something that can happen. You can go through your problem very carefully and we'll be in a situation where our variable is gone. So we're left to interpret our answer. One of our options is we get the same number equal to itself. Let's do this next problem. Let's distribute that 4. Distribute the negative 4 on the other one. And we're left with negative 3 minus 4x minus 24 is equal to negative 4x plus 4 equals 3. All right, let's try to get our x's together. Well, let's clean up our equal sign. So we have 3 minus 24 on one side and 4 minus 3 on the other side. Okay, let's move our x's. So we do plus 4x, that's gone, plus 4x, whoa, that's also gone. What do we have left? So my x's are gone, and we're left with negative 21 equals 1. Is that true? No, right? So we have a false statement. When you get a false statement, our answer is as follows. There are no solutions. Let's do another example. Solve 3x minus 8x plus 6 equals 4x minus 1 minus 5. So we have to start off by distributing what's outside the parentheses. So negative 8 times x is negative 8x. Negative 8 times 6 is negative 48. 4 times x is 4x. And 4 times negative 1 is negative 4. Let's go ahead and clean up the right-hand side and the left-hand side. On the left-hand side, I see I can take 3 minus 48. And on the right-hand side, I see I have 4 minus 5. All right, so now I have minus 45 or negative 45 minus 8x equals 4x minus 9. Let's go ahead and clean it up. Let's go ahead and add our constant to both sides. So plus 45, that's gone, plus 45. And we're left with negative 8x equals 4x plus 36. Okay, let's go ahead and move that 4x. So minus 4x, so that's gone. Minus 4x, negative 8 minus 4x, we're left with negative 12x. So I have negative 12x equals 36. Divide by your negative 12. And we're left with x equals negative 3. All right, let's go over about what we learned. An equation solving procedure. First, you want to clear the equation of fractions or decimals. If that is needed, this step is optional, but it can ease the calculations. So it's not necessary, but you can. So we saw when it was decimals, you multiply by your highest decimal holder. So tenths place, hundredths place. When you have fractions, you're going to multiply by your lowest common denominator. So you have to look at all the denominators and see which one works best. If parentheses occur, multiply to remove them using the distributive law. 3. Collect like terms on each side of the equation if necessary. 4. Use the addition principle to get all like terms with the variables on one side and all the other terms on the other side. 5. Collect like terms on each side again if necessary. And 6. Use the multiplication principle to solve for the variable. All right, that's it for this section 1.1.